dimension. So it's natural to ask the same question about Fermi liquids. So the low energy theory of the Fermi liquid has this big, huge symmetry, smooth maps from a circle to U1, and that has an anomaly. So you can ask, what's a higher dimensional theory for which this is the boundary theory, right? And so the answer turns out to be interesting. It turns out to be a theory in 4+1 dimensions. Now, how that comes about, the physics of it is simple, but initially you might be surprised by it because we're talking about Fermi liquids in 2 space dimensions, 2+1 dimensions, but yet the bulk theory, which combines with this theory so that the emergent symmetry has no, the anomaly of this theory combines with the bulk to make the theory completely ordinary, is a theory in 4+1 dimensions, not 3+1. And the way to think about this extra dimension is to really think about it as a theory in phase space, right? So phase space for a 2-dimensional system is 4-dimensional, and then there's time. So you should really think about Fermi liquid theory as a theory in phase space, and then, but where one momentum direction is singled out, the momenta are near the Fermi surface, and then the bulk theory is in 4+1 dimensions. And it's actually a very, very physical interpretation of this extra dimension in this context. You can just think about it as going into the interior of the Fermi surface, right? So in other words, this bulk boundary correspondence works, and you can think of it as working in the following way in the Fermi liquid. Low energy Fermi liquid theory lives at the Fermi surface, but then it's the boundary of the interior of the Fermi surface, right? So you can think of the interior of the Fermi surface as your bulk phase, to which there's a boundary theory, and there's a correspondence between the physics of the boundary and the structure of the bulk theory, right? I have a paragraph in the notes saying as much. I think it's a good thing for you to chew on. It's simple, but it's good to mull over the statement. Yeah.
You can say those words, but where's the space? Space never comes in. Coordinate space.
Right. So when you have 5 dimensions, 1 is time, 2 is real space, and 2 is momentum space.
Right, but what is the real space in the study of, let's say, fluctuations of Fermi surface?
Right. So if you have a long wavelength deformation of the system, right, of the low energy theory of a metal, right, where things can vary in space.
Oh, I see. So you picture like different.
Yeah, that's right.
In space, different Fermi surface configuration.
That's right. Yeah.
And does this counting work in 3 dimensions?
Yeah. So then the anomaly theory is in, the Fermi surface is 2-dimensional surface, right? But the anomaly theory is in 7 space-time dimensions. It's always a Chern-Simons theory in 2D+1 dimensions. So it's all, and you can work things out and everything fits in, just reproduces what we know about ordinary Fermi liquids, but from a different point of view. And perhaps it's useful somewhere.
Is there some bulk term?
Yeah, it's just a Chern-Simons term in 2D+1 dimensions, but with non-commutativity of the space. Yeah. All right, so let's change gears. Yeah. Yeah, it's a bit more subtle for composite Fermi liquids because it's a gauge field, right? So again, you had to ask whether it's the HLR theory or this Dirac theory, but let's do HLR. So there is a similar emergent symmetry, and it has an anomaly, and that again constrains many of the properties of the composite Fermi liquid. But it's extended. It's not just it's obviously not the same theory as the Fermi liquid because there's a gauge field. Right? The overall U1 generator is gauged, and because of flux attachment that's tied to the flux, so it gives you some extra structure.
Is there a way to think of the anomaly in the bulk? Complementary way?
Yeah, so that's this 4+1 dimensional Chern-Simons theory. right? So the usual Chern-Simons theory is in 2 plus 1. If you have a U1 gauge field in 4 plus 1, there's an A wedge DA term. That's the Chern-Simons theorem. And that all, so you can work things out. And these kinematic properties of the Fermi liquid can be shown to follow from this bulk Chern-Simons theorem. No, it's all abelian. The symmetry group is abelian, right? And so so you can give an interpretation of the various components of the gauge field as A0, AX, and AY. And then there's gauge fields with momentum space components. And you should think about that as the Berry connection in momentum space, right? So there's a Berry connection which has AKX, AKY. And there's an ordinary vector potential, which is AX and AY, and the scalar potential, which is A0.
X and P.
Yeah, so that plays some role in some things. There's actually a nice paper by someone who I thought was here. Can you identify yourself? You know who you are. It's Yizhuang Yu student. You have a nice paper. Yeah, that's you, right? So they have a nice paper explaining something that we made a guess for some property in our original paper, and they explained it as a consequence of the non-commutativity of phase space. Anyway, all right, let's move on to this new topic. So I want to talk about anyonic quantum matter. I should say that everything I had to say about this topic is things that I learned while working together with an absolutely wonderful student, Zhengyan Darius Shi, at least a former student. He's now graduated and is going to go to Stanford. And I also worked. We also worked with Carolyn Zhang, who's a postdoc at Harvard. So it's been a lot of fun. Yeah. So the question that will motivate this talk, unlike Steve, I didn't have time to prepare anything other than slides. So I'll use the board occasionally, but for the same reason as Steve, I'll mostly use slides. And Leo gave me permission to do that. So the question is about the physics of a many-body collection of anyons. Now, the first statement in talking about this, and one of the most important statements, is that anyons exist in real life, right? So that's a big deal, right? They're not just purely theoretical objects, but they exist as famously as emergent quasi-particles in the fractional quantum Hall effect. So in this entire talk, I want to discuss the physics of a many-body system of mobile anyons. Okay, and the defining property of an anyon, at least the usual kind of anyon, is that when you exchange two of them, the wave function acquires a phase, right? So now think about what happens if these things are mobile. They're trying to move, but each time there's an exchange-like process, the wave function picks up a phase, right? So that leads to frustration of the motion of these anyons. So what does this? So it's a highly frustrated liquid. So what does this liquid do in the ground state, right? And even more dramatically, the anyons could be non-abelian. I'm sure all of you have heard of non-abelian anyons. They have a huge internal degeneracy of the Hilbert space when they are sufficiently well separated. Now, at finite density, when you bring them together, that degeneracy will be lifted somehow by terms in the Hamiltonian. That's on top of the frustration coming from the braiding of anyons around each other, right? So how does all this happen at finite density?
Does fractional statistics frustrate motion more than other statistics?
Yeah, we don't know. We'll see.
Oh, okay.
Other statistics, boson motion is, you could say, not frustrated.
Right. So I wondered why it's not intermediate to fermion motion.
So you can ask whether it's intermediate to fermion motion or not, but the question is interesting. Right? It's at least it's more frustrated than bosons, and maybe as frustrated, if not more, than for fermions. We get lucky because the solvability of the ideal Fermi gas. Here, there is no such solvability. Right?
So when you bring them together, you're saying they will be interacting, and that the degeneracy, or is it?
Yeah, for non-abelions, that will be true. Right? So we want to ask the question: what are the ground states of quantum matter that's made up of anyons? Right? So let's start with the system where we know anyons exist for sure. It's the fractional quantum Hall effect. And the usual story is that you need a strong magnetic field in 2 dimensions. And of course, time reversal is broken. This is one of the most beautiful pictures in all of condensed matter, all of physics, I think. No, it's really amazing, right? And as you know, there are excitations at these fractions with fractional charge and fractional statistics. That's anyons. So that's the old story. Now, in the last 2 years, something very interesting has happened in this field. Several of you probably know this, but if not, let me tell you. There's a phenomenon called the fractional quantum anomalous Hall effect that's been discovered in these 2D Moiré materials. You'll hear a lot about Moiré materials next week, so I won't introduce them to you. Presumably, everybody knows that this is a field of research in condensed matter physics. Yeah? No? Wake up. Give me an enthusiastic yes. So this anomalous here refers to a situation where time reversal is present microscopically, but it's broken spontaneously to give you a Hall effect. That's a classic anomalous Hall effect. The quantum anomalous Hall effect is when this spontaneously broken time reversal enables the system to have a Hall effect that's quantized, right? And it's fractional because the Hall conductivity is fractional. So this occurs, and so these Moiré materials have lattices. This occurs in lattice systems where time reversal is broken spontaneously, and you get churn bands. And then you partially fill those churn bands you might get, and these experimental systems, you do get a fractional quantum anomalous Hall effect. Okay, so the system, for instance, in graphene, in some of these graphene systems, the microscopic system has bands in each of 2 valleys, which are related by time reversal, and the bands in either valley have churn number, and then due to interactions, the system spontaneously polarizes in valley space. So one valley is selectively occupied compared to the other, and that ends up breaking time reversal. And so at integer filling, you might just occupy one of these 4 churn bands, and then you get a churn insulator. But at fractional filling, the potential to get a fractional quantum anomalous Hall effect, right? So this was first seen in this system, twisted transition metal dichalcogenide, MOT2, 2 years ago by Shodong Chu and the Cornell group. And shortly thereafter, in multilayer graphene by my colleague Long Ju. There's both spin and valley ferromagnetism. So in graphene, you have to worry about spin. In the TMD systems, there's strong spin orbit coupling. So spin is locked to the valley at some very high energy scale. So spin disappears as an independent degree of freedom. So yeah, but there's ferromagnetism in the system, right? And so spin and valley polarize.
Twice field? The K point, right? Down is lower than up.
No. This is just my way of depicting degeneracy. It's maybe a poor way. We should have drawn it sideways. These are degenerate. Yeah, there's no split. Yeah. Sorry. All right. So let me show you some data. So this is Shodong Chu, and this is Kinfai Mark, Jishan. These are the real heroes in this field. These and Long Ju and some of the other experimentalists. So this trace is that lattice filling 2/3 of the Moiré bands. So there's a Moiré lattice, and that lattice is filled, it's in a valence band, but never mind. It's at a lattice filling of 2/3. This news should not be confused with Landau level filling. There are no Landau levels here, right? There's no external magnetic field. The nu just refers to the charge per unit cell. And at 2/3, so there's the longitudinal resistance as a function of field. It's not doing very much. It's close to 0. But the Hall resistance has a hysteresis loop. which suggests that time reversal is spontaneously broken. And beyond a coercive field, you get a Hall resistance of 3 over 2 h over e squared, which corresponds to a Hall conductivity of 2 over 3 e squared over h. Okay. And likewise at 3/5, and by now people see it at 4/7 and so on and so forth. Right. So this is the evidence for time reversal being broken spontaneously, and this is the evidence for quantization. Now, a similar phenomenon was seen by Longju at MIT in multi-layer graphene stacked in a particular way. It's called the rhombohedral stacking. And his setup was different. He needed a strong electric field perpendicular to the stack, and it was aligned with some substrate on one side and so on. But then here's a phase diagram as function of this perpendicular. It's called D because it's a displacement field. Displacement field and charge density. You see this, again, nu refers to the lattice filling. At nu equals 1, you see an integer quantum anomalous Hall state. At the lowest temperatures, you see this hysteresis and then quantization of Rxy at h over e squared. And at 2/3, you once again see hysteresis and quantization at 3 over 2 h over e squared. Right? And there's many more plateaus that are seen in this system, but for the purpose of this talk, all you need to know is that this phenomenon exists in real life. Okay. Yeah. Right. So this is the early data. This from his first published paper. Now, in subsequent devices, the RXX value has come down dramatically. So he thinks that the first experiment had some edge issues. There's some edge reconstruction or something. But as he makes more and more devices, the RXX has kept going down. By now, it's below a few hundred kilo ohms. Right? So it's very small. Sorry, a few hundred ohms. Thank you. Thank you, indeed. Okay. Wait, what am I doing? Yeah, so this is a new setting for the fractional quantum Hall phenomenon. People often ask, why is this interesting? Fractional quantum Hall effect exists for 40 years, right? What's the big deal? So I'll give you some of the reasons why it's a big deal. There are many other reasons why it's a big deal. But first, we have electrons on a lattice with lattice translation symmetry and time reversal symmetry. The microscopic system, lattice translation is a good symmetry, and there are block bands. So this is a sketch from the experimentalist paper of the microscopic band structure in MOTE2. There is a band structure, right? This, unlike the Landau level setting, the single particle problem doesn't have well-defined momenta, right? In the presence of a strong magnetic field. So time reversal is broken spontaneously. Now, lattice translation, we don't know directly from experiment, but from theory, actually, Aidan Reddy is sitting somewhere here. He's done a lot of good theory on MOTE2. Whatever modeling people have done, that it looks like lattice translation is preserved in the fractional quantum anomalous Hall ground state. It could have been broken, but you don't need it to be broken. And the theory supports the statement that it's not broken, right? So then you have an insulator, a novel insulator, which lives in 0p external real space magnetic field, may have Berry curvature or something, but lattice translations remain a good symmetry in the ground state, right? It preserves lattice translation symmetry, and that's new, right? We don't have that in the usual quantum Hall effect. So let's look at the excitations of this fractional quantum anomalous Hall state. Right, so it's magnetic translation symmetry, which is a different beast, right? There's continuous magnetic translation symmetry, but here there's ordinary, in the microscopic system, there's ordinary lattice translation symmetry. Tx and Ty just commute, discrete translations. Yeah, the Hall effect comes from a momentum space magnetic field, not a real space magnetic field. So K is a good quantum number. Okay, so now it's very generally true. And if I'd had time, I said I'll revisit the fractional quantum Hall. I didn't have time for that. It's in my notes. You can argue on very general grounds that the observation of quantized Hall conductivity without knowing anything about the microscopics, implies the existence of fractionally charged excitations with a particular fractional statistics. Right? This, for the charge, it's been known since Laughlin, so original paper, and for statistics, the understanding trickled in over the last several decades. There are many papers. Steve wrote a nice paper on this that he probably has forgotten in 1985. Yeah, so there's a set of nice arguments that lead you to establish this result. So as an example, at 2/3, 2/3 is the prominent state that's seen in all the experiments. Right? People don't see the 1/3 usually, right? But 2/3 is what's actually seen. So at 2/3, you have anyons with fractional charge 2e/3 and fractional statistics 2π/3. You exchange two of them, you get this phase. And this observation immediately implies that by fusing these, you can argue that you have other anyons with charge e/3 and statistics π/3. Right? So on general grounds, we can conclude that these excitations exist in the experimental system. Right? Now, on general grounds, you don't know which anyon is cheaper. Right? That depends on microscopic model. And one can try to do microscopic calculations, but in this talk, I'm just going to be somewhat focused on some universal aspects of physics. No, you don't want to do that. That won't change the topological sector. You can fuse two of these together to get the charge 4/3 anyon and then bind it to an electron. Yeah. So that will change the topological sector. Yeah. Okay. Yeah, actually, in my notes, I put up a very general discussion of this kind of thing for any filling P/Q, something that we did in a very recent paper. But in any case, for our purposes, this is all we need. So then one of the new features about the fractional quantum Hall in this setting is the lattice translation symmetry. Now let's ask how lattice translations act in the fractional quantum anomalous Hall state. Right? In the microscopic system, we have ordinary lattice translation action on electrons, right? There's discrete lattice translations, they commute, they have eigenstates that are labeled by Bloch momenta, and there are corresponding eigenvalues for the Hamiltonian, so on and so forth. Now, in the low energy theory, unlike in the fractional quantum Hall, this means that the charged excitation, which are the anyons, now have a well-defined dispersion in the Brillouin zone. Right? In the quantum Hall effect, that doesn't happen. In the Landau level quantum Hall effect, that doesn't happen. But here, the anyons will have well-defined momenta and well-defined dispersion. Now, not only do these anyons have fractional charge, but they also have, in a certain precise sense, fractional momentum. Okay, so let me explain what that story is. Yeah, I'm going to explain the words in these last few sentences. Let's see how it goes, right? Yeah.
So the low energy theory projected to some low energy band. Array system there, or is it like you're considering all the bands in the light microscope?
Yeah, I'm not specifying the microscopic Hamiltonian.
My question is, if I had like only one band and I project the position operator to a given band,
Right.
then the position operator might not. Right?
That's correct. Yeah. If there's a Berry phase, for instance, yeah, Berry curvature.
And we do have a Berry curvature.
Right, but so the situation here is more extreme than that, because I'm not talking about electrons. I'm talking about what happens to the anyons, right? Which are highly non-local objects in terms of the electrons, right? So let me give you this argument for why the anyons have some weird action of lattice translations. For the theorists in the room, it's what's called a projective action of lattice translations, as opposed to a linear representation of the algebra. And the reason is this. It's actually very physical. So what do we have in the system, right? We have a system in zero magnetic field. Maybe time reversal has been broken through ferromagnetism, but you still have, microscopically, you have translation symmetry. And it's a fractional filling of the band. right? So maybe I have a churn band and I have fractional filling of the band, right? And we are saying that there is a ground state that is gapped and preserves the discrete lattice translation symmetry, right? So how can that ever happen, right? Yeah, fractional filling, how can you have a translation preserving ground state that is gapped, right? So the usual band insulator, we know that we just place, 1 electron per flavor in each unit cell. But at fractional filling, if you try to arrange electrons themselves, you're inevitably, any classical arrangement of charge will break lattice translation symmetry, right? Now, the fractional quantum Hall state solves this problem very elegantly because in the fractional quantum Hall, you have excitations at fractional charge, right? So I have a 2/3 charged Anyon, and I can just place that in each unit cell, right? And that's a construction of a ground state, which is completely translation invariant, right? It's the emergence of this fractional charge that enables the system to have a translation symmetry preserving ground state at fractional filling.
That's those 2/3 particles excitation things.
Right, but once I have those kinds of excitations, right, I can see how I can stabilize the state as a translation symmetric state at fractional filling, right? Now, this statement is much, much more general than the particular example I'm talking about. There are very deep results that have been proven to satisfy what's called these Lipschultz Mattis restrictions for what kinds of gap ground states possible at fractional filling. And if you want a symmetric gap ground state at fractional filling, you always need fractional charge and associated topological order. So that's a general theorem. And we see how that worked out in the specific context. Yeah.
I'm not saying the ground state is a Mott insulator consisting of 2/3 anion, one on each side.
That's a construction of the ground state. Of course, you have to produce that 2/3 Anyon in the first place. So you need the topological order.
So you can view the ground state this way?
You can view the ground state as a Mott insulator of emergent anyons, which have somehow managed to emerge. Right? But they have to emerge in the first place, and there you need the topological order, right? So this construction just tells you how you can accommodate lattice translation symmetry into this fractional quantum Hall state. Okay, but
What are electrons?
the electrons are broken up into these fractions, right?
Well, like I think of loss in the wave function.
So you can write wave functions and so on, but yeah.
No, but it's something on top of the Laughlin wave function.
No, the microscopic is completely different. The wave function may have nothing to do with Laughlin at all, right? Laughlin wave function is something about the microscope. It's tied to the microscopic Hamiltonian and Landau levels. Here we are in a completely different context.
Certainly is a wave function.
There is some wave function. You can write down wave functions for this state. Yeah, so there is a construct. There are many constructions of wave
Is there
functions.
some slated determinant plus these guys?
No. So the right wave function will be some sort of projection of a product of slated determinants. So you can do a part-on construction of the wave function for whatever it's worth. Obviously, a wave function exists in terms of electric coordinates, but again, I can discuss physics like this without any reference to a particular microscopic Hamiltonian or a particular microscopic wave function. So these are very universal aspects of the physics, right? Such that you were telling me that there's someone here who doesn't like models. So I'm not using any models. So if that person were here, they'd be happy. Yeah. You had a question? No? Yeah.
Can we say that electrons are not fundamental because they break through?
No. Well, you can say whatever you want, but it may not be, it may be misleading. I mean, that's a general question about philosophical question about the fractional quantum Hall effect in the first place, right? Let's just focus on my system, our system, which is the new stuff in the fractional quantum Hall. Yeah.
It's the fact that the lattice translation is broken. That is why right?
Right. If lattice translation is broken, then I don't need to worry about how to accommodate it in the ground state, right? So this has a consequence, this observation. I'm going to illustrate it on the square lattice because it's easier for me to draw those pictures. But the Moiré systems are actually triangular lattices. But anyway, the same story will go through. I might fractionalize this. But so let's think about a square lattice. So in a band insulator, I would put an electron in each unit cell. Now I want to put 2/3 charged Anyon. So lattice filling, mu equals 2/3. So now I want to put a 2/3 charged Anyon at each unit cell of this lattice. Right? So let's say I put it here, for instance. Now I want to ask how lattice translations acts on some excitation in the system, which could be an excited 2/3 Anyon, or it could be an excited 1/3 charged Anyon, or something else, right? Now, so let's say I have a 2/3 charged Anyon that I've excited. Let's say I place it somewhere here, and I want to translate it. So this is Ty, Tx, Ty, Tx, Ty inverse, Tx inverse. So now what I've done is to taken this excited Anyon and braided it around the background Anyon. Then there's a braiding phase, which is e to the 4 pi I over 3. Right? So even though translations commute when acting on the electrons, they don't commute when acting on these Anyons. Right? And likewise, if I take the 1/3 charged Anyon, I'll have a similar effect. So I do the 1/3 charged Anyon. And I do this again. So now I have a braiding of the 1/3 Anyon with the background 2/3 Anyon. Then I once again get a phase, so Tx, Ty, Tx inverse, Ty inverse on, let me call it A squared. It's squared. It's really A squared times the electron, but topologically it's the same as A squared. Right? So either way, you say that translations no longer commute when acting on these Anyons. It's as though the Anyons now see a magnetic flux through each unit cell. But the flux is a rational fraction of 2 pi. Right? There's no external magnetic field, but the filling constraint, the fact that you're at fractional filling, generates these phase factors and makes the system behave as though it's seeing a magnetic flux. Okay? Yeah. So the braiding phase will be, it will be 2 times this, right? It's 8 pi over 3, which is 2 pi over 3 mod 2 pi. For the 1/3 Anyon, yeah. So this is the 1/3 Anyon, right? 2/3 Anyon, and then you remove the electron from it. The electron is local operator. You see, then hidden.
Can you say something more concrete about how Lipschitz-Mattis theorem does this? Like what's the concrete statement here of the theorem?
So the Lipschitz-Mattis Toshikawa-Hastings theorem is the statement that if you have any particles, bosons or fermions, and let's forget about spin, right? At fractional filling of a lattice, and you impose that the ground state preserves charge conservation and translation symmetry, and that there's a gap to all excitations, then the ground state must have topological order. Right? That's one statement that comes out of that theorem.
But there's some statement about
In 2 or higher dimensions.
But there's some statement about what type of topological order, or just the
Yeah, so that's known in many cases. That so there's a big theory of this. That so I just want to specialize to the particular problem. For bosons, there's a big statement that filling P over Q, there's a minimal topological order where you have at least, ZQ gauge theory if it's time reversal invariant or U1 level Q. If it's for fermions, there's a different story, and it's all, there are theorems on all of these things, most of which I don't need, so I'm not talking about it.
So I had a related question. This view of the ground state as a Victor crystal for Anyon. How do I see the topological degeneracy of the ground state?
Right, that comes from the fact that these anyons have emerged in the first place. The only thing that this view helps me with is to accommodate the translation symmetry, how this topological order helps.
So I have to, there's some topological fluid background.
Exactly, that's absolutely correct. Yeah, Hayden.
So my question is, I think about ordinary fractional quantum Hall state. I have an Anyon, and it's just, I take it around a closed loop in the absence of any other Anyons in the closed loop. Then I just think about it taking out the Berry phase from the magnetic field.
From the magnetic field, yeah, right.
But so I'm trying to reconcile, like, I want to be able to think about an ordinary fractional quantum Hall state as having some Anyons glued to every, like some background Anyon.
Yeah, yeah.
And then, but why don't I then get like a Berry phase coming from Anyonic statistics?
That's the same as what you get from the standard Arnaud-Bohm effect coming from the uniform field. Because in the ground state of the fractional quantum Hall effect, the flux is tied to charge. Right? There's this, it's like a Mort insulator, except that the charge is not tied to lattice sides. It's tied to the flux. Right? So there's 2 points of view on the Arnaud-Bohm phase that you first mentioned. One is just coming from the magnetic field. The other is that it's coming from the braiding with the background anyons that you can think of as having filled up the ground state, give you a uniform translation variant liquid.
Yes, maybe to think a bit more carefully about like how avoiding double counting or something like that.
Yeah, you're not double counting. Yeah, you should think it through. It's a good exercise, but you're not double
But
counting.
you do
Yeah.
one or the other.
You do one or the other. But here, there is no magnetic field, so this is the right point of view. Right? Yeah.
Just from your previous lecture, should I call this an anomalous translation symmetry or?
Yeah, so if you want to use those words, fractional filling on the lattice, you can think of it, the Lipschitz-Mattis constraint as coming from an anomaly in the UV theory of anomaly between translations and the global U1 symmetry. That anomaly is matched in the low energy theory by this projective action of translation. But Leo will complain these are highfalutin words. So let's forget about anomalies for now. One can rephrase all of these things in that language. Yeah.
But I do want to know those words because then
Later.
I will translate them to.
Right.
So when you construct one third and you put two thirds and you subtract an electron.
Yeah.
So but electron when two exchange has a pi phase. So does that show up? Does it show up?
Right. So this will get the right statistics of the electron. So statistics of this is 2 pi over 3. The statistics of A squared is 8 pi over 3. But then when you add an electron to it, you subtract a pi or add a pi, and that'll give you the right statistics of the charge 1/3 excitation. So you need that pi to get the right statistics of the charge 1/3 excitation. Yeah. Yeah. Sorry?
What do the excitations look like?
Oh, they're just the anyons that I described. No, this is the ground state, and the excitations are either charge 1/3 anyons, charge 2/3 anyons, or electrons.
By slides.
No. So this is the ground state, and then you can have excited states where on top of the ground state, let's say, for instance, one excitation could be an anyon anti-anyon pair, right? That will preserve the total on top of this. Yeah, that's right. Like in a Mort insulator or band insulator. Yeah.
So the ground state has translational symmetry.
Lattice translation symmetry.
Lattice translation symmetry. But you seem to kind of say that it's as though for the excitation, the translation symmetry is broken.
It's not broken. It's just realized in a projective manner.
I see.
Right? Again, since you work on spin liquids, an analogy will be that if you have a spin system with global SO3 symmetry, there may go to a spin liquid state, the excitations may have spin half, which is a projective representation of SO3. So here, likewise, there's ordinary translations on the local objects,
Yeah.
but on the anyons, there's projective
I see.
realization of the symmetry. Yeah.
So if you, let's say you make these guys flow, like you put,
No, there's a lattice. It's a commensurate Mort insulator.
okay, so let's say beyond, okay, I'm trying to figure out whether it's gonna be, your narrow band noise is gonna be a lattice level or.
No, it's commensurate. It's commensurate, right? It's a commensurate. If you want to think about it as a Wigner crystal, it's locked in place by a lattice. Homework problem for Leo. Yeah, that's right. Yeah, but I think so. But anyway, I'll leave that as a homework problem for you. Next Friday, you can submit the answer. Yeah. No, this is much more general than any construction. You can derive this answer through the composite fermion construction, through a composite boson construction, through wave functions, multiple points of view. But this is completely general, right? Yeah, but a composite fermion will nucleate the anyon. Composite fermions are not real particles. They are human-made objects, while anyons are real particles. Okay? Yeah. It's a big confusion in the quantum Hall literature. Yeah. No, so in some sense, anyons, even free anyons, there's a strong statistical interaction, right? So it's a many-body problem, even when it's a free problem, right? Again, we've been fooled by free fermions into thinking that we can solve the problem exactly. Right? Fermions also have phases, but luckily we have, or unluckily, because it's confused us, we get a limit where we can solve the problem exactly. For anyons, there is no such limit. Right? Anyway, but that's jumping ahead many steps, right? I'm still now just describing the properties of single excitations. Okay, so now the band structure of an anyon as an excitation in this state, the universal feature is that it transforms projectively. It has these projective phases under lattice translations, but corresponding to a rational flux through each unit cell. So clearly, if you go to 3 unit cells, there is no net flux. So on a 3x1 unit cell, the anyons will have a well-defined dispersion. But like in the Hofstadter problem, this means that you'll have 3 degenerate species of anyons that move in a reduced Brillouin zone, each of area 1/3 that of the original electron Brillouin zone. And there'll be a dispersion, right? So you have dispersing anyons that live in a reduced Brillouin zone with 3 species that have degenerate dispersions. Okay, so that's my description of the universal aspects of the fractional quantum anomalous Hall state. Yeah?
What exactly do you mean by this energy momentum?
Yes, that's right. It's the Brillouin zone that's fractionalized. That's right, yeah. So, yeah, fractional momentum really means that. All right, so let's summarize. So the fractional quantum anomalous Hall state is an insulator fractional filling of a lattice with a zero field fractional quantum Hall effect. The excitations are the anyons with fractional electric charge and a well-defined dispersion. So now we can ask about doping the state. And if we manage to dope the state, then we'll get charged anyons at a non-zero density. And anyons have kinetic energy, so they may become mobile. Then I have a mobile fluid of anyons, and I have to solve the problem of anyonic quantum matter. Yeah.
By removing some of the background charge from the background 2/3 flux and moving it around.
So that would be a hole-like excitation. You can also add a charge. So then that's an extra excitation on top.
Adding a charge like
You can either dope with positive charge or negative charge, like in any other insulator, right? You can do electron particle doping or hole doping, right? And in fact, you can do both. You can do either, and the answers could be different, like in any other insulator, right? Yeah,
Just to make sure, like the condition, yeah,
yeah,
costs quite energy, but like after you add whatever Anyon, then
exactly. But then when I dope, I'm tuning a chemical potential, and I'm forcing the system to have a finite charge deviation of the charge density from 2/3. Now I have finite charge density, and it may well be carried by the first excitations that carry the charge may well be anyons. Right? You would expect them to be anyons. So just
Exactly, so the dispersion of the
okay.
do you solve the many-body problem? Because now you cannot form any status term.
Yeah. So I'm coming to that. Yeah, that's the rest of the talk. And I don't know the exact dispersion of the anyons, but I'll still be able to say something. Right? Okay. So why is this question interesting in the first place? Right? Over the years, I've come to realize that you can tell people about your work, but they often don't pay attention unless you invest time telling them why you find it interesting. And maybe they'll also find it interesting. Right? So let me tell you why I find it interesting to consider this problem. So the first motivation is that doping correlated insulators is a cool thing to do in condensed matter physics. Right? There's this famous story, which we've been hearing about from Steve, cuprates, doping Mott insulators. And at low doping, the problem is that of a small density of mobile charges that moves in the background of the frozen charges of the Mott insulator, right? And we know we get ITC, we get pseudo gaps, we get stained metals, all kinds of interesting things. And you can think about the entire problem of cuprates, at least many of us like to think about it, as a fight between Mott, who controls the zero doping state, and Landau, who controls the heavily doped state. Right? So Mott focuses on the on-site U, Landau focuses on the hopping, and these two battle it out in the middle, and interesting things happen. Right? So now we have available, instead of an antiferromagnetic Mott insulator, we have available a truly exotic insulator with fractionally charged excitations. Right? So if we dope it, the quantum Hall effect, of course, we should replace Mott with Laughlin. If we dope it, eventually you might think that a Fermi liquid is competitive. Then you can see what happens if Laughlin and Landau fight it out. Right? So it's interesting. If you like fights, it's interesting. And so what is the fate of a small density of mobile anyons moving in the background of a fractional quantum anomalous Hall insulator? Right? So I thought this was an interesting question to ask. And equally importantly, I cut my teeth working on spin liquids. And we're always going and telling experimenters, oh, if you have a spin liquid candidate, just dope it. And they're horrified. It's not easy to dope. Tell them dope ruthenium trichloride, come back in 5 years, maybe. In Moiré, it's just very easy. In these 2D materials, it's very easy to dope. People do it routinely, right? You just tune some gate voltages and boom. So here's examples of phase diagrams in twisted MOT2. This horizontal axis, the density. So you're changing the density with gate voltages, and the very first experiments produce a phase diagram. Likewise in multilayer graphene and so on. You can just tune it with voltages, right, with gates. So it's really easy to dope these systems.
Do I get Anyon doping by just like adding magnetic fields at finite magnetization density?
You can do that, absolutely. Yeah. In fact, we're trying to do some DMRG on precisely that problem. But you first have to find the spin liquid, right?
But you think you electron dope, like here you're doing electron dope.
Absolutely, yeah. You're doping charges into the system, and it's routinely done, right? So doping is trivial in the Moiré context, experimentally.
No, but the idea is you dope, and then these electrons now become these, effectively becomes like Anyon doping.
That's right. That's right. That's the hope, right?
Somehow you want not to destroy the states completely and go to Fermi liquid.
Right. Yeah, that's the hope, indeed. All right. Now, the third motivation actually goes back nearly 40 years. It's the same Laughlin, but are there ideas of the same Laughlin? right? So way back in 1988, he had this idea that a mobile fluid of anyons will actually go superconducting. Okay? And he was thinking about cuprates, and it was an attractive, beautiful theory of the cuprates, but it was already abandoned by the time I started graduate school in 1992, right? Because experiments were nowhere near supporting it. So this came to be known as Anyon superconductivity, a fascinating idea which had no relevance to anything in condensed matter physics till now. Okay, I actually don't like the term Anyon superconductivity, as I've been ranting to several people. I think it's better to call it Anyon-driven or Anyon-induced superconductivity. But in any case,
Your case, not the old case, or the old case too.
the old case too. In condensed matter physics, microscopically, we only have electrons or bosons. Anyons are always emergent particles. Well, some of that old literature, people thought of anyons as fundamental particles in the universe, and that's just wrong.
Just said that composite fermions are human-made anyons or particles.
Anyons are real excitations. They are physical excitations. Composite fermions, it depends on who. It's my construction. Why are they better than composite bosons? They are all equally valid constructions, right? What I can go and measure is an anyon, right?
The superconductor, ordinary, that's the point.
Ultimately, any phase of matter we get is a phase of matter of an underlying electron system. That's a theorem.
But you say that even if it's Anyon driven, like that you're trying to accomplish, the superconductor will have ordinary it's going to be.
It'll have an order parameter and so on and so forth, ignoring the dynamical U1 gauge. Yeah. Sorry, who's speaking? Hold your breath. If I can get to it, I'll answer that question. That's a very interesting question. So this is a paper that Laughlin wrote in 1988. Cuprates were discovered fall 1986. And this is a remarkable paper, right? The two biggest, most striking things that were discovered in the 1980s, he thought that they were somehow closely related, right? I read this as an undergrad trying to decide what part of physics to go into. And then I decided condensed matter physics is it. It's really beautiful stuff. And the key sentence is somewhere here that particles carrying a fraction of an elementary quantum number attract each other by a powerful gauge force, which can lead to a new kind of superconductivity, right? So I'm not really going to explain this paper or anything. There's a very important, at least a very influential later elaboration by these authors. They probably coined the term Anyon superconductivity. There's lots of good ideas in this old literature, but when we revisited them starting a couple of years back, we realized that there are all kinds of statements that are probably misleading at the best, or probably just incorrect at the worst. So it's better to think it through afresh. After all, we are 35 years older and wiser, right? So let's just think it through afresh. Yeah.
You raising of the fraction with the gauge force.
This is just for motivation. I'll talk about the theory.
Yeah, the question about this for electrons for a Fermi liquid, I can show that the bound state has lower energy than just two electronic excitations on top of the liquid. Can you do the same for?
Yeah, for the case that Laughlin was originally considering, you shouldn't think of it as binding of anyons with anything else. Okay, so it's a gas of semyons, and this gas of semyons goes superfluid. Right? There's no it's no sense in which you're binding semyons. That's the wrong picture. Since I haven't talked about the theory, I can't really explain it, but yeah, that's not the right picture. Yeah. No. So I'm not saying which ideas need to be refined. That'll require me to go too deeply into this literature. I just want to say that there's some inspiration, right? Now let's just do theory with this as inspiration, right? There's many of the statements in this paper, in particular, there's a statement that this superconductor has no order parameter, and it's not, as a state of matter, just completely different from an ordinary superconductor. And that statement is wrong. There's also statements about flux quantization here that are incorrect, at least with the naive interpretation. You know, it's like it's like some Picasso painting. You can give it an interpretation by which you can make it right. Okay, so let me describe what the status was in one slide, right? So it was inspired by the cuprates, and it was abandoned early because there's no strong signature of time reversal breaking. Right? So people did experiments, no strong T breaking, and then they said, that's not relevant, let's move on. Now, so forget about cuprates. We know that there's fractional quantum Hall, which has anyons. Cuprates, start off as antiferromagnetic Mott insulators, not as chiral spin liquids or whatever. But then in the FQAH realization of anyons, the anyons move in cyclotron orbits, which means that their kinetic energy is strongly suppressed. Right? So when you move away from the center of, from say 2/3 or 1/3, the anyons get localized, you just get a fractional quantum Hall plateau. And then if you increase the density more, you go to the next plateau. Right? There's a plateau transition, and that's it. The anyons are not very mobile. Right? Now here, so that's all that happens in the standard realization of anyons in condensed matter. But now we have this new realization of anyons, where we expect that the anyons will have a well-defined momentum and dispersion. So this gives us a great opportunity when we dope the system to study the physics of a mobile fluid of anyons. Okay, so that's the new, one of the new things made possible by the discovery of the fractional quantum Hall effect in these lattice systems in the last 2 years. Okay. All right, so many people have asked me questions about what I'm supposed to do when I don't know the exact dispersion, or even if I knew it, what am I supposed to do? So how should we study it theoretically, right? Now, you could do numerics on microscopic models, and people are in the process of doing them right now, but that's not what I did, or what we did in our group. It's hard, right? You have to do DMRG, and it's a hard numerical project. But we can make progress analytically by using a low energy effective field theory for the fractional quantum Hall state. Right? For the regular fractional quantum Hall state in Landau level, there's well-known effective field theories, Ginzburg-Landau theories of the fractional quantum Hall phenomenon, originally due to Steve and Shuqing Zhang and Hansen, and using composite bosons, and by Lopez and Fratkin using composite fermions. Right? So we want to use the similar kind of Ginzburg-Landau theory to describe the parent state, and then use that Ginzburg-Landau theory to go away from the plateau and ask what happens when you dope. Right? And we also have to modify this description to include the lattice translation symmetry, which is a new ingredient now. Okay, so an example of this kind of Ginzburg-Landau theory using some kind of fermions instead of bosons, right? So essentially, you should think of this as representing the anyon as either a fermion or boson that's coupled to other fields that are such that if this field is a static source of those other fields, it transmutes itself into an anyon. Right? That's the general idea behind these Chern-Simons Ginzburg-Landau theories. So I've written a Lagrangian here with the field psi, 3 species, psi I, 3 species, I goes from 1 to 3. Psi I is the fermion that will evolve into the anyon, into the charged 2/3 anyon, if the system is in the 2/3 fractional quantum Hall plateau, right? And this field is electrically charged. It couples to the external electromagnetic gauge field, but it also couples to an internal dynamical U1 gauge field, which I'm calling B. And this B has a Chern-Simons action, Chern-Simons Lagrangian, and this B is also coupled to the external electromagnetic field. The last term just represents an integer quantum Hall response. Really, the rest of the Lagrangian. So you think of the 2/3 states as an integer quantum Hall state plus a 1/3 state of holes. So it's a 1/3 Laughlin state of holes. And this last term just describes the integer, the filled land, the filled Chern band. Yeah.
Could you repeat what you mean by the fermion that evolves into the Anyon?
Right. So in the state, this field, right? So low energy theory is just described by the remaining 3 terms in the Lagrangian. So now imagine you have a localized source of that there's a fermion that's you localize somewhere, maybe with the local potential, right? So that fermion is charged under this field little b, right? So if you write the equation of motion for B0, then you'll see that there's a 1/3 flux of little b, 1/3 magnetic flux of the internal gauge field that's nucleated by this charge. And that 1/3 flux gives you an electromagnetic charge of 1/3. So this fermion becomes an Anyon.
So it's not to be thought of as related to the electron.
It is related, if you wish, there's a bit like a composite fermion, right? It provides a field that you can construct for the fractional quantum Hall state to describe the fractional quantum Hall state.
I mean, like the regular electrons, they don't have this flux and
Yeah, that's right.
There should only be one electron.
That's right. So this thing, regular electrons or local objects, they are gauge invariant objects, meaning you can create them locally, right? You can tunnel with a metallic tip. Anyons you can't. So this object is not gauge invariant. It couples to an internal gauge field, so you can't create it locally too. So this object has the potential to evolve into an Anyon, and that's exactly what happens. Yeah? Sorry? Oh, sorry. Yeah, I lifted this from a different talk where I described the integer quantum Hall effect using the C gauge field. I forgot to erase the C. Thank you. Yeah. So if you've seen Ginzburg-Landau theories of fractional quantum Hall, or if you know about the Chern-Simons description of fractional quantum Hall, this will make sense to you. Otherwise, just accept it. It'll take me too long to extend. It's a full lecture in itself. It's a beautiful story, but yeah. Right, so the 3 species, so that the translation action will mix these 3 species. Right, so the microscopic translation action acts in this low energy theory in some way, and that some way will encode the projective action of translations of the microscopic translation symmetry. Yeah?
There any dictionary between this microscopic theory and this gauge field?
Absolutely. So every local operator in this field theory can be interpreted as a microscopic operator in the original system.
What would that look like?
Right. So the gauge field itself is not gauge invariant. Local operator means gauge invariant objects, right? So you can ask about operators that create 2 pi flux for little b. Those are monopole operators, right? So those things will correspond to charged excitation. They'll correspond to the electron, in fact, right? So this operator should create 2 pi flux of b that creates, 3 anyons, and so that'll be an electron. So in this theory, that'll be a charge 2 Cooper pair, but yeah. Yeah.
So the system is time reverse symmetry breaking. You
Yeah.
do it, you create some sort of superconductor. Would that
No, we have not yet gotten there. And it's not, I'm not saying you will create a superconductor. Let's see what we create. That was inspiration. Yeah, that's it. All right, very good. Sorry? Oh, I'm using the notation of differential forms. So dB is, its components are, curl B. Yeah, just think of it as curl B. Right? Yeah.
Solvable is not solvable. Like the tie-up or something.
Yeah.
Anyon's always exactly localized, so we can't think about it from that perspective.
No, they're not I mean, in the Kitaev model, if you're talking about the Kitaev honeycomb model, the M particle is exactly localized because no dynamics there. But if you perturb the cation model a little bit, the M particle will have dynamics. It'll have a dispersion. Yeah.
So can we think about like Anyon doping?
So doping requires a conserved global U1 charge. In the cation model, you don't have that. You can enrich the cation model to construct a different model with the global U1 symmetry, and then you can talk about such things. Right? But for now, let's just focus on the system that actually exists in experiments. Right? Yeah.
So here you have the third, all the things like it would be quite a bit different for 1/3 percent.
Yeah, so we've analyzed all the Jane fractions. We've also analyzed all the Reed states, to get different answers in each case. Yeah, but let me just focus on 2/3. Okay, so if you know the Chern-Simons description, you understand this intimately. If you don't know the Chern-Simons description, just take a coarse-grained view of what's in the slide. There is some effective field theory for the quantum Hall state. It's like a Ginzburg-Landau theory, and we're going to use that to study the effect of doping. Yeah. Yeah, so that's not a question for effective field theory, right? That's a question for microscopic theory. Now, yeah, so that's beyond the scope of an effective theory. That's something that you have to look at microscopic models, do calculations, and indeed the kinds of things that Aiden, for instance, does in MOT2. I think there is from the microscopics, it does turn out that you see 2/3, 3/5, and so on, but you don't see 1/3. But that's beyond the scope of what I'm talking about. Right? My focus is something else. Okay, so let me first give you the results, and then I'll give you explanations of the results. Right? So let's see what we get if we do this. When we dope the charge 2/3 Anyon, suppose that's how the charge goes in terms of charge 2/3 Anyons, then it turns out that the answer is a superconductor. It's a charge 2 superconductor. Various people were asking me. And it's a superconductor that's smoothly connected to a BCS superconductor. Okay? And the only mildly topological thing about it is that it's what's now called a topological superconductor. It has 4 neutral Majorana edge modes. So this then gives us a realization. If you tune the chemical potential, you go from this 2/3 quantum Hall state, and if you dope this charge 2/3 Anyon, you get beyond the critical chemical potential, you get this chiral topological superconductor, right? And this occurs, and maybe that's why someone was asking, this occurs in a system which is strongly time reversal broken. It has no Fermi surface in the normal state. You should not think about this as a BCS instability of a Fermi surface. But the ground state, nevertheless, is smoothly connected to something that you could have obtained in some totally different regime from a system with a Fermi surface to a BCS instability, right? So again, as many people were asking, at the end of the day, there's an electron superconductor, right? If the only thing you knew is if the only experiment you ever did was sitting right out here, and you never knew what was living here, and the only experiments you did were long wavelength, low energy experiments, you would not know that there's anything beyond BCS in the system. Yeah.
Is it a singlet?
Yeah. So the spin is out of the picture in this entire story, right? And that's well motivated from experience in MOT2. Spin is anyway locked to valley, and you're valley polarized. And if this applies to rhombohedral graphene, there's a lot of evidence that it's spin and valley polarized. So we can forget about spin. So spin is not a degree of freedom. Yeah. Yeah.
You are saying if it's smoothly connected to a BCS superconductor, but we'll not get a part.
Right. It's smoothly connected in the space of Hamiltonians. Right. The space of Hamiltonians is vast. There's an infinite number of terms you can write in the Hilbert space. Right. So I don't know what terms you have to tune to reach the weakly coupled BCS superconductor. In a way, it's not that different from the cuprates, where you have the overdoped superconductor, which, as Steve said, you can understand within renormalized BCS theory. There's the underdoped superconductor, which you presumably cannot understand that way because normal state doesn't have a normal Fermi surface, but the ground states are smoothly connected. There's no phase transition. There need not be a phase transition inside the superconducting state.
But smoothly connected to a topological BCS superconductor?
Yeah, absolutely, yeah. Yeah.
This theory, you have to include pairing directionally to derive that.
Yeah, I'll talk about that a bit later. Yeah. There is a place where some sort of pairing is implicitly assumed. I'll return to that. Yeah.
Can you call it thermal gas of
Yeah, eventually to have a gas of anyons and you go up to high enough temperature, right? The statistics cannot matter beyond the thermal de Broglie, whatever. When the thermal de Broglie wavelength becomes order interparticle spacing, then it's a Boltzmann gas. Yeah. Not the line, of course. The existence of it can be inferred, but you need some non-universal information. You need the effective mass of anyons and things like that. Hold your breath. I have 15 minutes. If I don't get to it, ask me during question time. The anyons don't. There's an ordinary superconductor, right? But it's a really interesting question to ask what happened to the anyon when you went superconducting. There's a beautiful answer to that question, very subtle. Okay, so that's one possibility that you get a superconductor in this very non-BCS route to a superconductor, but a superconductor that at the end of the day is very tame, right? I don't want to say it's boring, but it's tame, right? Okay, now I don't want to call this an Anyon superconductor because it's, after all, it's smoothly connected to BCS. It's confusing to call it Anyon superconductivity. I want to say the anyons play a role in the mechanism to stabilize the superconductor, but at the end of the day, it's just an electron superconductor. Now, you can ask what happens if you dope the charge 1/3 anyon, and within the same theoretical framework, you don't get a superconductor. At least that's not the most natural state. Instead, you get a Fermi liquid. Okay? And this Fermi liquid, coexists with the CDW, which enlarges the unit cell by a factor of 3. Right? So it's a commensurate CDW. There's a doping-induced CDW whose period is not changing, but whose amplitude is increasing. Right? And it has an interesting evolution in the theory. There's some composite Fermi liquids at intermediate temperature. But at the end of the day, as far as the ground state is concerned, this is the natural possibility. It's a more exotic possibility, but the natural one is to just get a CDW metal with Fermi surface's area counts the deviation of the charge from 2/3. Right? So this is also a conventional ground state emerging in an unconventional way. Right? So there's another reason why I don't want to call the superconductor an Anyon superconductor. Then for consistency, I'd have to call this an Anyon liquid, which sounds cool, but it also sounds ridiculous. Yeah.
Or you deviate from being commensurability 3, stronger the commensurability 3.
Absolutely, yeah. Exactly, yeah. That's right. Of course, eventually, you'll destroy the correlations that give you the fractional quantum Hall, and so there'll be a dome. Yeah? It will, yeah. There's very curvature in the bands. We'll definitely have that. And all it's all conventional physics, right? In the end of the day, you get a conventional state, which you can describe without any of these fancy objects, anyons, this and that. But that's the ground state. The mechanism to stabilize it involves all these weird objects. Okay. So let me give you some insight on where you get the superconductivity from first. And then I'll sketch a couple of equations. And then we'll talk about experiments and some of the very subtle aspects of the physics that Leo was asking me to address. So when we dope the charge 2/3 anyon, I said you get a superconductor within this effective theory. So let's think about how to think about the fluid of charge 2/3 anyons, right? So the assumption is that the charge 1/3 anyon is a big gap, and that gap is not closing. But at low energies, the only thing that charge has entered the system in terms of charge 2/3 anyons and have a mobile fluid of charge 2/3 anyons, right? Now let's ask the following question. What is the smallest electrical charge that I can add to the system locally coming from the external world, right? In the external world, I don't have anyons. I only have electrons or composites of electrons, right? So I definitely can't add a single charge 2/3 anyon. That's not a locally creatable object. It has fractional statistics, it has fractional charge. Now I can also not add 2 charge 2/3 anyons because that also has fractional charge and fractional statistics. It's not a local object either. But if I think about 3 charge 2/3 anyons, that has charge 2, and you can convince yourself by looking at how things braid that it braids trivially with everything else. Right? So 3 charge 2/3 anyons is just a Cooper pair. Right? So in this fluid, you can't add single electrons at low energy. Right? If you come in with an ordinary STM and try to tunnel electrons, you won't be able to tunnel electrons at low energy. You have to go above the 1/3 anyon gap. Right? So you need to have a finite bias voltage before you can get any tunneling.
What would happen if you focus on 2/3, but you also had a 1/3 possibility? You could tunnel 3
1/3 anyons. That's an electron.
And
it
would be a superconductor.
Yeah. So let me address that in 10. Give me 10 seconds, Leo. I'll go back to the previous slide and we can. But for now, let me focus on the slide. Right. So in this fluid of 2/3 anyons, I can't add single electrons at low energy. I can't tunnel in at low bias with an STM tip, with a metallic STM tip. But if I come in with a superconducting tip, I stole this slide from Seamus Davis's website. He does have a superconducting tip. Okay, let's imagine it's spin valley polarized, blah, blah, blah. But conceptually, you can tunnel in with a superconducting tip, right? The system can accommodate Cooper pairs at low energy, but not single electrons. So really, you can think of it as a charge 2/3 anyon fluid, but a different point of view on the same system is to say it really is a fluid of Cooper pairs. Those are the local charged objects that exist at low energies in the system at finite density. And of course, a fluid of Cooper pairs will give you condensation into a superfluid. Yeah.
I know you can only tunnel in pairs of electrons.
Yeah.
Why do they have to stay bound in triplets of anyons once they're inside the?
Yeah, so I haven't told you what the theory actually does, right? But this gives you, this to get you some intuition, right? Ultimately, I have to analyze the effective field theory, right? Okay.
So you said at the beginning that the choice of ratio of the cheaper anyon is like a 2/3 or 1/3.
It's energetics, yeah.
It's like energy for microscope.
Yeah.
So how would this picture change if I switch 2/3 to 1/3 in this case? That would be like 1 electron instead of Cooper.
Yeah, so since both you and Leo asked this question, let me go back to the slide that I showed. You get a metal. It's a Fermi liquid metal. And this metal, of course, is low energy electrons. So at 1/3, you can create an electron at low energy. So perhaps it's not surprising that you get a metal, right? Yeah, so then everything.
So it's very natural. If 2/3 is lower, then Cooper pair is lower than an electron.
Exactly, yeah. That's right, yeah. Okay, let me just sketch this field theory derivation. Yeah.
Yes, anyone's defined together to cancel the braiding phase. Where is the first one?
Yeah, so you could try that intuition. It's a good path to go in, but it's a wrong path. That intuition, it turns out, is completely wrong, right? Because if that's what was going on, the 3 anyons bind together into a Cooper pair, and that's the superconductor, then the topological order will survive, right? But the superconductor we are getting is not topologically ordered, right? So that intuition is not the right intuition. Okay, so I'm just going to sketch this. I'm running out of time anyway. Again, for those of you who know the Chern-Simons theory, this is just a few steps. If you don't, wake up in 1 minute. Okay, so we started with this Lagrangian. So really, we have the undoped system has these Anyon bands at finite energy, right? Like in any other insulator, the charged excitations form some band above a gap. And here we dope it. We dope it like in any other insulator. The chemical potential will now cut through the band. But unlike in any other insulator, these fermions at finite density will now, because of the Chern-Simons interactions, they'll see a self-consistent magnetic field. And in that magnetic field, they'll form Landau levels, right? So you can work it through in the theory, and it turns out each species of these fermions is at a Landau level filling of -1, and they form an integer quantum Hall state. And you can work with that, with the theory of the integer quantum Hall state, and you end up with this low energy theory where now you can do the integral over B and you'll get a Meissner effect for the background gauge field, right? And by keeping track of the edge states, there's a very mechanical way to keep track of the edge states by coupling a metric to this system, but I'm not indicating that. You can look for thermal edge currents by keeping track of a metric. You can show that it's a chiral topological superconductor with 4 minor edge modes. So that's the rough sketch of how the effective field theory calculation works. Yeah. Yeah. Why? And the fact that you have one-way minor edge mode already requires breaking time reversal, right? That when I say counterpropagating, the statement is that they are going in the opposite direction compared to the charged edge mode of the parent fractional quantum anomalous Hall state. Okay. Yeah, so I'll just leave it at this. It may make sense to some people, but the calculation is not long. It's very simple. Yeah. Right, so my general convention is that anything in small letters is dynamical, anything in capital letters is a background, right? Yeah?
So you have a Meissner effect just because the integrating B out forces TP, TA to be 0.
Exactly.
But there's still like this chiral term.
Yeah, so once A is 0, this doesn't matter, right? And the 2 here tells you that it's a charge 2 superconductor.
The third term.
The third term, only have 2 terms. Oh, that, as I said, I'm just.
No.
So it's 3 over A
3
minus
over 4,
B.
no, 3 over 4 pi. No, the next one.
Oh, this one.
Came from Fermi and
Exactly. That these form an integer quantum Hall state, right? And there's 3 of them, each at Landau level filling -1. And that cancels the self-Chern-Simons term for B. So that's a technical part of the story. I don't have time to talk about non-abelians. These have not been seen in experiments so far in Moiré systems at 0 field. But, again, I'll point to Aidan, who says that maybe you will see them. So maybe you will. I believe Aidan all the time. Sorry? Yeah, no, you're good. But then it's just a fun theoretical question to ask about what happens when you dope a non-abelian quantum Hall state, right? So we can answer that with the effective field theory approach. It's now a much more complicated effective field theory that involves a U2 gauge field with Chern-Simons terms, but we can handle all that. And at the end of the day, for Murid, you just get, once again, a superconductor that's smoothly connected to a BCS superconductor. And that was more interesting for the Reed-Desai states, but there's a method to analyze all of these. So I have just a few minutes. So let me not dwell on the non-abelian thing other than to tell you that we know how to handle it within the effective field theory. Let me instead talk about experiments. So I gave this talk where I forget where. Actually, this note of last month. This is actually from the Steve Kivelson's 70th birthday conference. That was in March. It was in March. So when I gave some version of this talk in March, this is what I said. The existing platforms, there's twisted MOTE2, which has the parent fractional quantum Hall states. But TMDs have a lot of disorder. You need to control the disorder. Measuring transport in TMD is hard. There's big contact resistance, and to do it at low temperature is hard. So I was somewhat pessimistic, I think. I thought it will take many years for people to improve all of these. I was also pessimistic about rhomboidal graphene aligned with HBN because all the fractional quantum anomalous Hall physics is seen on the Moiré distant side, where there's this alignment with the substrate, but you drive the electrons far away from where it's aligned. And those electrons on the far side only see a weak periodic potential, right? And you need that periodic potential to give the anyons enough mobility. So I thought this was maybe not great. And now my colleagues, Longju and Rayashuri, on the Moiré proximate side, they also saw an FCI state that's stabilized by a small magnetic field. And that has a strong periodic potential. And I thought, okay, maybe that's where you might get something, blah, blah, blah. But I was proven wrong. In early May or maybe late April, there was this paper, April, I guess, from Xingxin Li, somewhere in China. And this is on twisted MOT2. He had a really good device, see quantum oscillations and things like that. And right next to the 2/3 state, there's a tiny region of what seems to be a superconductor, right? It occurs in a range of displacement field where at 2/3, you get the fractional quantum anomalous Hall state. And away from 2/3, you get this tiny region of superconductivity. So here are the line cuts of the resistance. The rho XX is 0 here, close to 0. And it's 3 over, rho XY is 3 over 2. As you go towards nu equals 1, you see that there's a peak in rho XX. And then at the lowest temperatures, it seems to go to 0. And rho XY, retreats from this plateau and approaches something close to 0, right? So it's a signature of a superconductor. So as an experiment, whatever the theoretical explanation is, the experiment is pretty cool, right? You have fractional quantum Hall and superconductivity existing right next to each other in the same device. Yeah. At nu equals 1, why would you not call it a superconductor? Oh, in any quantum Hall state, rho XX is 0.
Sure.
Right? Here, rho XY is also 0 in this region. Right? Yeah. Okay, so can we declare victory? That's the real question. And I don't think I want to declare victory. It's encouraging, but you have to be very careful before claiming victory, right? First of all, this signature of superconductivity occurs close to the fractional quantum Hall state, but it's separated by a big resistive peak, right? And it's a crucial question whether the normal state out of which the superconductor arises, what its carrier density is. Is it large, meaning it's a deviation from filling 1, or is it small? Is it the deviation from filling 2/3, right? As of now, from the data, we don't know the answer to this question. Okay. So we can make some intelligent guesses based on what we know from the theory that I told you about. I mean, let's see whether we can accommodate what's seen in experiments on the basis of this theoretical framework that we have, whether or not it's the right theory, right? So a couple of papers by us and by Nosov, Han, and Khalaf at the same time that made these guesses. So when you evolve out of the 2/3 state, now in the experiments, the signature of superconductivity is seen only on one side. When you go towards nu equals 1, it's not seen on the other side when you go towards nu equals half. So we say, okay, maybe when you go towards nu equals half, you're doping the charge 1/3 Anyon. When you go towards nu equals 1, you're doping the charge 2/3 Anyon. We have no microscopic reason to suspect this, but phenomenologically, if this happens, we can accommodate the phenomenology, right? And because it's a real system, the doping-induced transition, we have to include disorder, right? There's no way to meaningfully discuss this evolution without thinking about disorder. And you can think about disorder, and the answer depends on whether the disorder is in the form of point defects or in the form of smooth disorder, smooth on the Moiré scale, and so on. And from talking to many of the experimentalists in the field, it seems to me that one could make a case that the disorder is more of the smooth random potential variety. People have worked very, very hard to get to rid MOT2 of point defects, but we don't know whether that's true. But then there's some sort of superconductor insulator transition, and it will have, according to standard theory, a universal resistivity tensor at the critical point at the delocalization transition. And with rho xx and rho xy both of order h over e squared. And so perhaps that's the peak that you see in the experiments. The peak height is of order 10 kilo ohms, which is a fraction of h over e squared. So maybe that's what it is, right? But people have to study the temperature dependence of the peak height and peak width and so on. And we don't have that. We have some results on the temperature dependence, but we don't know whether the height saturates at low temperature.
There's no linearities.
There should be large non-linearities are seen in the superconducting state.
No, vortex glass. That would distinguish it from
Right, I haven't yet talked about the vortex glass, but I will. Actually, I don't know. It depends on whether. Yeah, I can easily finish in 5 minutes unless Leo asks me a lot more questions. All right, so let's talk about the question that Leo and other people brought up. So this entire theory for the superconductor induced by doping this state, I said you get a conventional charge 2 superconductor. So then you have to ask, how does flux quantization work? People ask me this question every time I give a talk. And Leo just asked me, right? So the answer turns out is very, very interesting, and it's subtle. It's actually not dissimilar to what Steve was saying about doping a Z2 spin liquid and getting a superconductor and how you get H over 2E flux quantization. It's a variant of that, but a much more subtle variant of that. But the answers are clear. So Leo's question was, what happens to the anyons when you go into the superconductor? Right? And the answer is that the anyons become vortices of the superconductor. In particular, the charged 2/3 anyons. So the thing to imagine is, imagine you do this in a disk with a hole in the middle, and you thread an anyon through that hole, and then you evolve from the fractional quantum Hall state to the superconductor. Now, what state of the superconductor are you reaching? Right? And the answer is that if what's being threaded is a 2/3 anyon, then you get a superconducting vortex with vorticity 2 pi for the Cooper pair phase. So it corresponds to a plus h over 2e vortex. But this is true only mod 6 pi, meaning it could also nucleate a minus 4 pi vortex. Right? The 6 pi periodicity is perhaps not surprising if you know about the fractional quantum Hall effect. The ground state is periodic only after 6 pi flux insertion, not 2 pi. But then you're inheriting it into the superconducting state. Now, the 1/3 charged anyon goes into the superconducting vortex with minus 2 pi vorticity, mod 6 pi. So these two are not degenerate, and that's fine because you don't have a system that's time reversal symmetric. Right? So the core energies of these two vortices will be very different in the bulk, and each one originates from a different anyon in the parent state. And this understanding has some very subtle but important consequences for this anyon delocalization transition out of the fractional quantum anomalous Hall state in a disordered system. Okay, so in a disordered system, what will happen is that if you go exactly away from 2/3, the first anyons that go in are going to localize, right? And that's what gives you the finite width to the quantum Hall plateau. And so you can call it an anyon glass, much like the Bose glass or something in the superconductor insulator transition. And now you have, as you add more anyons, you'll eventually have a delocalization transition where the next anyons you add form a mobile fluid. But this is happening in the background of localized anyons, right? A glass of anyons. Now, we already saw that anyons become vortices in the superconductor. So when you have an anyon delocalization transition out of an anyon glass, you get a superconductor in the presence of finite density of localized anyons, but these localized anyons will transmute into vortices. So you get a finite density of localized vortices. Now, energetically, the system wants to have net neutral vorticity. It costs too much energy to have finite vorticity in zero field. There'll be logarithmic energy cost. So what the system will do, if you start with the localized set of 2/3 anyons, is that 2/3 of these vortices will be plus 2 pi. The remaining 1/3 will be minus 4 pi, right? And the energy cost of this configuration will be the phase stiffness times the log of the log of the density of the localized anyons, while the energy gain, there's an order 1 energy gain from the random potential, right? So long as the phase stiffness is small, which it will be near the superconducting transition, you'll always get a vortex glass. And this vortex glass in 2D was studied 35 years back, again in the cuprate context. And it's known that there is no finite temperature KT transition because there's thermal creep of vortices, collective rearrangements of the vortices that give you a resistive state. It has nonlinear IVs at a very temperature dependent scale that, roughly going like T cubed, above which you get nonlinear IV characteristics. Now, I don't want to show the data. If you look at the actual data on MOT2, the resistance goes to zero only very gradually. It's not doing a BKT type thing. And if you look deep in the supplementary of the paper, they show the IV curves. It's a mess, right? It's seriously nonlinear. At first, my reaction was, oh, it's the first experiment. The data will get better. But now I wonder whether it's an intrinsic feature of the physics. But I don't know. It may also be due to mundane reasons. Maybe the contacts are bad. Yeah.
So are you saying when you're doping out of the quantum Hall effect, you both adding electrical carriers, but then to make the superconductor, but you're also adding effective flux? Well, it's like the HC1 transition.
HC1.
Meaning you're entering the superconducting state.
Yeah, I don't have an external magnetic field.
I know, but the carriers you're adding, they're also these anyons you're saying look like flux.
For other anyons, yeah.
For other anyons.
That's right, yeah.
So I'm trying to understand whether you're coming from HC1 or HC2. But
there is no, it's in zero field.
No, I know.
Right?
But if charge carriers carry
no,
flux, that's what I mean.
No, but the flux, you should really think about it as canceling out in total.
I see.
So there's no net magnetic, otherwise there's big supercurrents, right? There's log L energy cost. But if you have canceling vorticity, then you only have log 1 over the interlocalized particle spacing.
Vortex glass of vortices that are plus or minus, on average is 0.
+1 and -2.
Okay, but in the right proportion.
The right proportion. So we call it an anomalous vortex glass. I had a picture somewhere. Yeah, maybe I tried to cut and paste something else, but I failed. So the story is that you go from this state, which is the plateau, fractional quantum Hall plateau, through an anomalous vortex glass to this chiral topological superconductor, which will have a finite temperature transition. So let me just stop here. There's other experiments in the field. There's a particularly interesting experiment by Longju without Moiré in 4-layer and also 5-layer rhombohedral graphene, which shows strongly time reversal broken superconductivity. I don't think what I've been talking about is directly relevant to that, but it's in the same general genre of strongly time reversal broken superconductivity. There's various other related papers. Luke has a paper with Chogang on related topics, and Stefan is somewhere. He has a paper on related topics. Ashwin, Yohi, and I already mentioned Islam Khalaf. Let me stop there.
Just a couple of quick questions, and then we'll actually continue discussion at the next session in the discussion. Yes.
So I assume that the zero temperature phase transitions are first order.
No, in a disordered system, they will be second order.
Okay, is there any notion of like what happens at like the critical point then?
Yeah, so when we have a notion, yeah, in the sense that no. So the one way to think about it is that it's as though it's at some mean field level, the description of this phase transition is like a quantum Hall plateau transition, right? But then you have to take that mean field description and couple it to gauge fields, right? That part of the story is very similar to how people, including Steve, long back, tried to describe the fractional quantum Hall plateau to plateau transition. And think of it as at some mean field level, some integer quantum Hall transition, and then you have to do gauge fluctuations on top of that, right? So here it's the same thing, except that the interpretation of one of the mean field integer quantum Hall states, after you include fluctuations, it's interpreted as a superconductor, right? But we, over the years, it's a large number of very general statements that we know how to make about these various kinds of plateau transitions, that the structure of the universal physics is clear. I can't calculate exponents or anything. No.
Last one.
If I were to consider the limit, I would think that with a 1/r interaction for small doping of anyons, they would form a bigger.
That's right. Yeah, absolutely. Yeah.
What sense is this not completely consistent with the experiment? You see the resistive peak, it could be a bigger.
No. The Wigner crystal, once it gets pinned, that's just the fractional quantum Hall state.
I see. So if I go, so I would just get a larger plateau and not the higher.
Exactly. Yeah. Exactly.